The concept of time travel has always captivated the human imagination. From the earliest myths and legends to the latest science fiction blockbusters, the idea of moving through time has been a source of endless fascination and speculation. From H.G. Wells's groundbreaking novel The Time Machine, which first introduced the concept of a machine that could travel through time, to the countless stories that followed, time travel has remained a popular theme in literature and film. Christopher Nolan's visually stunning Interstellar took this fascination to new heights, exploring the possibilities of time dilation and the effects of gravity on time. The film's depiction of time travel is rooted in real scientific theories, making it a compelling blend of fiction and reality. These stories ignite our dreams of witnessing historical events firsthand or catching a glimpse of the future. They allow us to imagine what it would be like to experience different eras and see how the world has changed over time. But could time travel ever be more than just a figment of our imagination? Could the science fiction of today become the science fact of tomorrow? Modern science, particularly Albert Einstein's groundbreaking theories, suggests that time travel may not be as far-fetched as it seems. Einstein's theory of relativity revolutionized our understanding of time and space, showing that they are interconnected and can be warped by gravity and speed. Could we one day step out of a time machine, just like H.G. Wells's intrepid time traveler? While this may still be a distant dream, the scientific principles that underpin the concept of time travel are very real. Einstein's theories provide the framework for understanding the nature of time and its intimate relationship with space. His equations showed that time is not a constant, but can be stretched and compressed depending on the conditions. His work laid the foundation for the physics of time travel, a field that continues to intrigue and challenge scientists to this day. Researchers are constantly exploring the possibilities and limitations of time travel, seeking to unlock the secrets of the universe. While the idea of hopping into a time machine and traveling to the distant past or future remains firmly in the realm of science fiction, the reality of time travel is far more subtle and nuanced. It involves understanding the complex nature of space-time and the ways in which it can be manipulated. It's not about DeLoreans or phone booths, it's about the fundamental nature of the universe itself. Theoretical physicists are exploring concepts like wormholes and cosmic strings, which could potentially allow for time travel under the right conditions. Our journey into the science of time travel begins with understanding Einstein's revolutionary ideas about space and time. These ideas have opened up new avenues of research and have inspired generations of scientists to explore the mysteries of the cosmos. These ideas, once considered radical, have become cornerstones of modern physics, guiding our exploration of the cosmos and shaping our understanding of the universe's most profound mysteries. As we continue to push the boundaries of our knowledge, who knows what discoveries await us in the future? The dream of time travel may one day become a reality, transforming our understanding of time and space forever. Albert Einstein, a name synonymous with genius, is often celebrated for his groundbreaking contributions to science. His theory of general relativity revolutionized our understanding of the universe, challenging the very fabric of reality as we knew it. This theory, put forth in 1915, proposed a radical concept. Time is not absolute but is interwoven with space to form a four-dimensional fabric known as spacetime. This idea was a departure from the Newtonian view of a static and unchanging universe. Imagine a trampoline as a representation of spacetime. The surface of the trampoline is like the fabric of spacetime, flexible and responsive to the objects placed upon it. Placing a bowling ball, representing a massive object like a star, on the trampoline creates a dip or a curvature in the fabric. This visual analogy helps us grasp the concept of how mass influences spacetime. This curvature is what we experience as gravity. The more massive the object, the deeper the curvature, and hence the stronger the gravitational pull. Einstein's theory states that massive objects warp the fabric of spacetime. This warping is not just a theoretical concept but has practical implications for how we understand the universe. This warping not only affects the path of objects but also influences the flow of time. Objects moving through this curved spacetime follow paths dictated by the curvature, which we observe as gravitational orbits. Time, according to Einstein, is not a constant but varies depending on the strength of the gravitational field. In stronger gravitational fields, time moves more slowly compared to regions with weaker gravitational fields. In regions of strong gravity, such as near a black hole, time slows down relative to regions of weaker gravity. This means that an observer near a black hole would experience time at a different rate than someone far away from it. This phenomenon, known as time dilation, is one of the most intriguing predictions of general relativity and a key concept in the quest to understand time travel. Time dilation has been confirmed through various experiments, including those involving precise atomic clocks. Einstein's theories, once considered radical, have been validated by numerous experiments and observations. From the bending of light around massive objects to the precise measurements of time in varying gravitational fields, his ideas have stood the test of time. Today, they form the bedrock of our understanding of the universe, from the behavior of galaxies to the very nature of time itself. The implications of general relativity continue to inspire and challenge scientists, pushing the boundaries of our knowledge and opening new frontiers in the exploration of the cosmos. Einstein's theory of relativity tells us that time is not absolute, but is relative to the observer's motion. This groundbreaking idea revolutionized our understanding of the universe. This means that time passes slower for objects moving at high speeds compared to those at rest. The faster you move, the slower time ticks for you. This phenomenon, known as time dilation, is not just a theoretical concept but a measurable reality. Scientists have conducted numerous experiments to confirm this. Consider astronauts aboard the International Space Station, orbiting Earth at a staggering speed of 17,500 miles per hour. At such high velocities, the effects of time dilation become more pronounced. Due to their high speed, astronauts on the ISS age slightly slower than people on Earth. This means that if an astronaut spent a year in space, they would return to Earth having aged just a tiny bit less than their friends and family. While this difference is minuscule, it is measurable with precise atomic clocks. These clocks are so accurate that they can detect even the smallest variations in time. Even at the speeds we travel in our everyday lives, time dilation plays a role. Though the effects are incredibly small, they are still present. Passengers on a jet plane, for example, experience a tiny amount of time dilation compared to those on the ground. This means that during a long flight, passengers age just a fraction of a second less than those who remain on the ground. While this time difference is incredibly small, it demonstrates that time dilation is not limited to the realm of science fiction, but is an inherent aspect of our universe. It shows that our everyday experiences are subtly influenced by the principles of relativity. These examples highlight a fascinating aspect of Einstein's relativity. Time is not a rigid, unchanging entity, but a fluid concept that is influenced by motion and gravity. The faster you move, or the stronger the gravitational field you are in, the more time will stretch or compress. This flexibility of time, as we will see, has profound implications for the possibility of time travel. If we can manipulate speed and gravity, who knows what the future holds for our journey through time. Section 4. Atomic clocks and jet lag, proof of time dilation. The concept of time dilation, while mind-boggling, has been experimentally verified numerous times. One of the most famous experiments, the Hafele-Keating experiment, provided compelling evidence for Einstein's theories. In 1971, physicists Joseph Hafele and Richard Keating flew cesium beam atomic clocks around the world on commercial airliners. They synchronized these incredibly precise clocks with a stationary atomic clock at the United States Naval Observatory. Upon their return, the clocks flown around the world showed a slight time difference compared to the stationary clock. The time difference, while incredibly small, precisely matched the predictions of Einstein's theory of relativity. This experiment, along with numerous others, provided irrefutable evidence that time is not absolute, but is affected by motion and gravity. The implications of this experiment extend beyond theoretical physics. It demonstrates that time dilation is not just a scientific curiosity, but a real phenomenon that affects our everyday lives, even if we don't directly perceive it. Section 5. GPS, navigating the space-time continuum. Perhaps the most tangible example of time dilation's impact on our lives is the Global Positioning System, or GPS. This ubiquitous technology, which guides us, tracks our deliveries, and even helps us find our lost pets, relies on the principles of relativity to function accurately. GPS satellites orbiting Earth carry atomic clocks. These clocks, due to their high altitude and speed, experience time slightly differently than clocks on the Earth's surface. To ensure accurate positioning, GPS satellites must account for this time difference known as relativistic time dilation. If GPS systems did not account for the effects of relativity, errors in positioning would accumulate rapidly, rendering the system useless. The fact that GPS works seamlessly is a testament to the accuracy of Einstein's theories and highlights the profound ways in which relativity impacts our daily lives. GPS is a remarkable example of how a seemingly abstract scientific theory, relativity, has led to the development of a technology that has become indispensable to modern society. It underscores the interconnectedness of scientific discovery, technological innovation, and our